In this lesson, we are going to discuss collisions. At the end of this video lesson, you should be able to differentiate elastic and inelastic collisions and describe the momentum of objects in a collision. From our previous discussion, we observed how momentum and impulse are evident on the collision of two bowling balls. We know that objects in motion such as these bowling balls have kinetic energy. We also know that for these objects to move, a certain force must be acted onto the object. The integral of a force applied to the objects is the impulse which changed the momentum of the objects. However, even when in collision, these objects conserve momentum. When objects like these balls collide and bounce off of each other after collision, the collision is said to be elastic. We can use the analogy of an elastic rubber band which does not change its size, shape, and mass after being forced. In this type of collision, no deformation happens on the objects. Thus, the individual masses of the objects are conserved. For the conservation of momentum on elastic collisions, since the object's masses do not change and are separated after collision, their masses are accounted individually or separately. Thus, we do not combine their masses. We follow the law of conservation of momentum formula, which describes that the sum of the products of the masses and velocities of the objects before collision is equal to the sum of the products of the masses and velocities of the objects after collision. Let us look at an example for elastic collision. A 0.02 kg ball moving to the right at 0.25 meters per second makes an elastic head-on collision with a 0.04 kg ball, which is initially moving to the left at 0.15 meters per second. After collision, the 0.02 kg ball moves to the left at 0.16 meters per second. What is the velocity of the 0.04 kg ball after collision? This is an example of elastic collision because the objects move separately after the collision and no deformation occurred on the objects. Let us identify the given quantities in this problem. For the mass of the first ball, we have 0.02 kilograms. Since it is moving to the right before collision, its velocity will be 0.25 meters per second. For the second ball, it has a mass of 0.04 kilograms. Since it is moving to the left at 0.15 meters per second before collision, its velocity is negative. The 0.02 kg ball then moves to the left at 0.16 meters per second after collision. Thus, it has a negative velocity. We are asked to solve for v sub 2 prime. For the solution, we are going to use the law of conservation of momentum formula for elastic collisions. To initially isolate v sub 2 prime, we subtract both sides of the equation by the product of the mass and velocity of ball 1 after collision. Lastly, we divide both sides of the equation by the mass of the second ball. Plugging in the values, we are going to have this expression. We are going to cancel the unit for mass because the mass in the denominator will cancel the mass in the unit for momentum in the numerator. Thus, the velocity of the 0.04 kg ball after collision is 0.06 meters per second. Since it is a positive sign, that means that it is moving to the right. This agrees with the separation of objects after elastic collision. Another type of collision is when either or both of the colliding objects is or are deformed. This is what we call inelastic collision. The important event here is the deformation of the objects after collision. Since their masses are not changed and the objects move separately, we account their masses separately just like for elastic collisions. The last type of collision resembles inelastic collision except for the direction and motion of the objects after collision. In this car crash, the two objects stick together and move with a common velocity. Also, both objects are deformed. This is what we call perfectly inelastic collision. In perfectly inelastic collisions, the total momentum before collision is the same as the combined momentum after collision as an isolated system. It is described as the product of the mass and velocity of object 1 before collision plus the product of the mass and velocity of object 2 before collision being equal to the combined masses of the colliding objects multiplied to their velocity as they move as one after collision. Let us look at an example for perfectly inelastic collision. A 0.25 kilogram arrow with a velocity of 15 meters per second to the east strikes and pierces a 0.06 kilogram apple. What is the final velocity of the combined mass? We know that this is a problem involving perfectly inelastic collision because the arrow and apple moved as one during the collision. Let us identify the given quantities in this problem. For this example, let us denote the arrow as object 1 and the apple as object 2. The arrow has a mass of 0.25 kilograms and a velocity of 15 meters per second. Its sign is positive because its movement is to the east or to the right. On the other hand, the apple has a mass of 0.06 kilograms and is at rest. Thus, its velocity is 0. For the solution, we are going to use the law of conservation of momentum formula for perfectly inelastic collision, which shows the combined masses after collision. Since we are looking for the final combined velocity, we need to divide both sides of the equation by m sub 1 plus m sub 2. Plugging in the values, we cancel 0.06 and 0 in the numerator and all units for mass. Answering this, the final combined velocity of the arrow and the apple is 12.10 meters per second. This answer is accurate because the mass of the arrow became heavier due to the apple. Thus, the velocity will be slower. To conclude this lesson, let us review the following concepts. Elastic collisions allow two objects to bounce and move separately after the collision. In inelastic collisions, the two objects deform during the collision but move separately after the collision. And lastly, in perfectly inelastic collisions, the two objects stick together and move with a common velocity after the collision. Both objects are deformed. And that ends our discussion on collisions.